Hey, JD from fluxfocus. Haven't done a video for a while. Just show you some stuff I've been playing around with. So I'll do a little video on coils and cores that I've been playing with. I won't go into everything about coils and cores because I'll be here for ages if I try to do that. But I'll just talk about a couple of cores that I've got here. So there's sort of two families of cores that you generally look at, and that is ferrite, and this is a ferrite toroidal core, and there's also powder iron cores. But even when you look at ferrite cores, from the manufacturer, if you're lucky, they'll tell you exactly what type of ferrite it's using, and that's usually specified in the material or the mix, and that's usually given a number. So when you're looking at cores, you sort of look up the manufacturer's tables of all this sort of stuff. So there'll be the size. This particular one is called FT23, F for ferrite, T for toroidal, and 23 is a sort of a standard size. For small cores that you might want to use, there's maybe 10 or 15 standard sizes that specify the outer diameter, inner diameter, and the height. And so that size coupled with the material or the mix, between those two things, plus when you're designing these, you want to know for good Q what sort of range of frequency is it going to be good for, and that'll be specified in there as well. And for this one here, this has got a initial permeability of 5,000, and once you start using it, depending on what you're doing, that permeability can increase. To help you figure out how many actually this one for ferrite, it's millihenries per 1,000 turns, and so that's given a number that's usually designated a designator AL in formulas, big A, little l, or big A and sort of a subscript L. What else about this particular one? Yeah, so a mix of 75 with that. This has got an AL of 2000. So as far as pretty much all cores go, for getting the most microhenries or millihenries, this value of core is very efficient. So in this case, I've got 28 turns on this core, and that's measuring 1 millihenry. So I started out with this core, and I thought, well, I'll just wind it up to about a millihenry. And so you can, if you think about that, I'm not going to do the I'm not going to embarrass myself by doing the maths, but so what does that make it? 50 something microhenries per turn. So you can get up to a high value without having to do too many turns. But for this gauge wire, it's not going to be a very powerful, you won't be able to pass too much current through it, but for the applications I've been doing, it's all low power stuff. So that is that one, and there's a whole bunch of different cores, right? So I'll show you the difference between that, and I'll put another, give me a second here, I'll put another ferrite core on the meter here. And so this core, the size I think is 1 or 2 sizes up. This is not easy with one hand. Alright, so this core I think is no, it's just 1 size up, and I've got the same number of turns on it, and it's a ferrite core, but as you can see, it's a lot lower value. So you can do, for this sort of core, you might want to have a more accurate value, so the resolution in turns is a lot better. Again, it's a ferrite, so that's usually specified in millihenries per 1,000 turns. This one has good Q at 80 to 180 megahertz. So that's another example of the sort of range of frequencies I'll specify. And this one's got an initial permeability of 20. And the mix for this one's called mix 68. And the millihenries per 1,000 turns is 9. So you can see the difference there between an AL of 2000 and an AL of 9. Gives you a much lower value per turns. And this size is an FT37, so the numbers go up as the size goes up as well. I'll take that one off and I'll put a powder iron core on there, which is the same size core as that last one. Now for the ferrite cores, because of they're all the same colour, but the powder iron cores, again I'm having trouble here doing this with one hand, give me just a second. The powder iron cores are colour coded, which is very handy. So for the frequency range for good Q, that's well, it's indicating the material mix and therefore the frequency range that they're good for good Q. So this one's red-white, so that means that it's good for 0.1 to 3 megahertz. Its initial permeability is 25. The AL for powdered iron, that's specified usually as microhenries per 100 turns. So for the formulas, that's a little bit different for the powder iron cores. And in fact, you probably have to double check the manufacturer's specs, because I've seen some documentation that suggests that sometimes that's specified as nanohenries per the number of turns squared. So if you're using one formula for a particular core that you only had half the specs on, and it comes out with the wrong or a value that you didn't expect, it's probably because it's not specified in the same way as the majority of them are. And I'll show you the value for that one. It's a little bit more, but really these two, even though the difference there is because they're for different frequencies, and this tester I think is probably only testing somewhere between 600 kilohertz and a meg. So that's sort of the difference between those two. But really, if you have a look at the difference between the I've written them on the packets. The AL for the last the ferrite was 9, and for this one is 90. But because of the way that they're specified, the millihenries per 1,000 turns and the microhenries per 100 turns, that's why they're very close in value. So here's the sort of table that you're going to want to have a look at for if you have a particular core and you're trying to figure out what it is, or if you want to design something you want to figure out what core you should be using. Over there on the left is this is the ferrite table, so the sizes on the left there for ferrite toroids, and going across is the materials and mixes that are available in this range, and on the far right is the actual dimensions of the core. And where those two intersect is the AL value, in this case for ferrites, the number of millihenries per 1,000 turns. And up here is a formula to help you out. You can flip this formula if you want to solve for millihenries, but here it's solving for the number of actual turns that you would use on the toroid for a given millihenry value. You can see there's quite a range there of in the mixes, what you might use them for and what sort of resolution you'll get for the number of turns on it. So you can see mix 75 and 77, get more microhenries and more millihenries for each turn. But really, for each turn, it's really going to be microhenries, but lots of them. And 43 is not bad as well. But all the other ones are a little bit lower. And I'll move up to the powder iron cores, and the ALs here are specified in again microhenries per 100 turns. For this manufacturer, that's what they've specified them in. And there's a few more sizes in this table, but you can see that as far as mix 26 isn't too bad, but a T400 core is pretty big. So for a low number of turns for a high value of inductance, these aren't so good, but these are better resolution if you're looking for a very specific value of inductance, so they're better for that, right? And you can see there the ranges of frequency that you'll get for decent Q, and you can also see there that each of the mixes has been given a different color, and that's fairly. I've never heard of manufacturers going outside of those colors. I don't think they'd be able to sell their cores as well if they did. Alright, well that's about it. Thanks for watching.